equal to 1/2. Now I'm going to take the second derivative, f double prime of x. Going to be 12 times 2 is 24x minus 6, which is 6 times 4x minus 1. And then you set second derivative equal to 0. You got 4x minus 1 equal to 0. So x is equal to 1/4. This will be the point right here. The point of inflection. Okay? Now we're going to make the table, the sign table a little bit more general. We're going to add another line for second derivative. I'm going to rewrite the table for you guys with one more line added. X going from negative infinity to positive infinity. F prime, f double prime, and the function f. Now we have three values to plug in. X equal to 0, x equal to 1/2 for the critical value, 0 right here, 1/2 right here. We also have x equal to a quarter for the inflection point, or point of inflection, 1/4 right here. For the line f prime, 0 right here, 0 right there, we did that already. Positive, negative, and positive. For f double prime, it's going to be 0 right here, and try. And x is less than 1/4, so x equals 0. This is negative, and the other side going to be positive. X is bigger than 1/4. So x is 1. It's going to be positive. Okay? So of course the graph is going to be like this. Go down right here, go up right here. Okay? And this point right here. From here to here, the graph is concave down. From here to here, the graph is concave up. So by looking at the table, even though I still don't have the exact graph for my function, but at least by looking at the table, I get a bunch of information. I can tell you that the graph will be increasing when x run from negative infinity to 0. And then the graph will be decreasing, next from 0 to 1/2. And then get back to be increasing when x from 1/2 to infinity. About concavity, I can tell you that from negative infinity to 1/4, the graph will be concave down. And then from 1/4 to infinity, the graph will be concave up. And I plan to do graph, you see something like this. Concave down, point of inflection, concave up. You have a local max, you have a local mean. Okay? And this idea is going to apply to all kind of graphs you can have. Of course, algebra may be different. It could be harder, it could be easier. But the idea is this. Show you another example, easy one. F of x equal to x squared minus 4x plus 3 then. I say it's easy because you guys learned about this function already. This is a quadratic function. The graph would be a parabola with positive leading coefficient, so it's going to be upward. So going to be decreasing, hit the bottom, local minimum, and increasing, concave up all the time, right? Now let's see how it works. Let's circle the domain. Domain is all real number. Okay? First derivative, 2x minus 4. X squared is 2x, 4x is 4. So 2x minus 4. This is 2 times x minus 2. And you set derivative equal to 0. And you have x equal to 2. And this is your critical point. Okay? Of course, later on you know that your critical point will be a minimum. And then second derivative, f double prime of x. This is 2x minus 4. The derivative is going to be 2. 2 is always positive, so for sure it's concave up all the time. Second derivative positive, concave up. All right, so let's make a table. We have only one values right here. Right? X from negative infinity to positive infinity. All right. F prime, F double prime, and then F. Only one value, 2. X equal to 2. F prime is 0. x is less than 2, say 0 or 1, 0 right here, so 2 times 0 is 0, minus 4, negative number, positive number. Okay, and f double prime is always positive, doesn't matter what. F prime is negative, the graph going down, get down to 0, and then after this, f go back to positive. So at least you have to sketch a graph, tend to go down first and then go up. And by looking at a table, you can tell right away this point right here will be your local minimum, local mean at x equal to 2, and this local mean value is equal to f of 2, which is 2 squared minus 4 times 2 plus 3 is equal to negative 1. Okay? And the graph is always concave up. Always concave up. Okay? And I claim that with this type of technique, you can take care of many functions in our text, any exercises. All right, and we can talk about what limit, and that we covered already in the limit section. When you want to find the asymptote, say the horizontal asymptote, you take the limit when x go to infinity or negative infinity. If that limit equal to constant, then yes, you do have a horizontal asymptote. Vertical asymptote, you take the limit when x approaches a constant. Okay? And usually you're going to have asymptote when you work with rational functions. But anyway, those are the main idea for the 2 sections. On 4.3, it showed you 2 tests. The first derivative test and the second derivative test. And then the 4.5, they put the 2 tests into a particular problem. Any problem show you how to use the 2 tests to figure out the local max or local mean. And talk about critical value and inflection point of inflection. Okay, and then you can roughly sketch a curve. And that's pretty much for the video clip today. Once again, in here I can only show you the main step, right? And this is mathematics, as you know. We need a lot of practice to master your skills. So please spend some time and practice. If you have any question, don't hesitate to shoot me an email. I'll try my best to answer you as quick as I can. Thank you for watching, guys. Have a good day.